Calculate the loop inductance per kilometer of a single phase transmission line comprising of two parallel conductors 1 meter apart and 1.25 centimeters in diameter. Also find reactance if frequency is 50 Hertz. So what do we have to find here? First we have to find the inductance per kilometer, okay, and then we have to find out the reactance, which is nothing but 2 pi FL. Now what is this expression? We will take the generalized formula for the inductance, 2 into 10 to the power minus 7 ln GMD by GMR. This is per conductor, right, for each of the conductors. But how many conductors we have here? Two conductors which are in series, right? So what will be the total inductance? This is going to be 2 times the inductance of each conductor. So it will be 4 into 10 to the power minus 7 ln GMD by GMR. So we first have to find out GMD and GMR. Once we find the inductance, frequency is anyways given, we will calculate the inductance, so we can find out the reactance. So first we will see the geometric mean distance. It is given that the single phase transmission line has two conductors which are 1 meter apart. So here you have one conductor, this is the second conductor, and the distance between these both is 1 meter. And 1.25 centimeters is the diameter. So what will be the radius? This is going to be 1.25 by 2 and centimeters. So see that this is in centimeters, this is in meters. So the GMD of each conductor will be, for this conductor it is going to be the distance from this conductor to the other conductor, which is nothing but 1 meter. So GMD is equal to 1 meter. So this is the geometric mean distance. Now what about the geometric mean radius? This is going to be the self radius, right? So GMR is R dash. This is equal to 0.7788 into R. So this is 0.7788 into radius is 1.25 by 2. So this is going to be 0.486 centimeters you are going to get. So the inductance is going to be L is equal to 2 into 10 to the power minus 7 ln GMD by GMR. So this is going to be 2 into 10 to the power minus 7 ln, here it is 1 meter, but we are converting into centimeters, okay. So this is going to be 100 centimeters divided by 0.486 centimeters. Here you can convert into meter also. So if you can keep this as 1, then 0.486 into 10 to the power minus 2 you can write here, okay. It is going to give you the same thing. Now this value if you calculate, you are going to get 10.653 into 10 to the power minus 7 Henry per meter, okay. Now this is the inductance for each conductor. So what will be the total inductance? So it will be twice of this value, right. So this you are going to get 21.3 into 10 to the power minus 7 Henry per meter. But in the question they have asked the inductance per kilometer. So we have to convert now this Henry per meter into Henry per kilometer. So how do you do this conversion? Henry per meter you can write as Henry by meters. 1 meter in kilometer is 10 to the power minus 3 kilometers, okay. So this is equal to 10 cube Henry per kilometer. So what is the conversion factor here? 10 to the power 3. So you multiply this by 10 to the power 3. So you are going to get 21.3 into 10 to the power minus 4 Henry per kilometer. Next, what is left out? The reactance. This is going to be 2 pi FL. So 2 pi into frequency is given as 50 Hertz into the inductance is 21.3 into 10 to the power minus 4. This will be what? Ohm per kilometer. Okay. So this you are going to get 0.669 ohm per kilometer. This is the reactance. A 3-phase 80 kilometer long transmission line has its conductors of 1.0 centimeter diameter spaced at the corners of the equilateral triangle of 100 centimeter side. Find the inductance per phase of the system. So here the 3 conductors are equidistant from each other, and what is this distance? It is given as 100 centimeter, right? And what about the radius? The diameter is given as 1 centimeter. So the radius, if you are going to take as r, then r is equal to 0.5 centimeters. Now we have derived the formula for the 3-phase system which is equilaterally spaced already, right? So the expression is 2 into 10 to the power minus 7 ln d by r dash. Never forget the dash, okay? So here d is the distance between each of the conductors. Now this formula you can substitute the values, you know d, you know r by dash, you can get it easily, okay? But we will try to do it by the GMD and GMR method, because in that way you don't have to remember the inductance for each and every different case, right? In the previous question also we have used GMD, GMR. Here also we will try to see if we get the same expression when we are using this concept. So here the geometric mean distance between it is between each of the phases. So if you take one phase, then the distance with this conductor, this is the other phase, second phase, and with the third phase to the power 1 by 2, because there are two distances involved. So d into d to the power 1 by 2. This is equal to d. And what about the geometric mean radius GMR for each phase? Here, since there is only one conductor per phase, the GMR is nothing but the r dash. So here you can see that the same expression is coming, 2 into 10 to the power minus 7, GMD is d, GMR is r dash. So it is the same expression, okay? So if you remember this formula, you will automatically get for every case. So if you substitute these values, then you are going to get inductance is equal to 2 into 10 to the power minus 7 ln, you can take in centimeters, if both are in centimeters it is enough. So 0.7788 into 0.5. What is the unit here? Henry per meter, right? Per unit length. But here what they are asking the entire inductance per phase for the 80 kilometer long line. So you just have to multiply with the length, okay? So inductance per phase for entire length of the line, this is going to be 2 into 10 to the power minus 7 ln 100 by 0.7788 into 0.5 into 80,000, right? Because 80 kilometers we want in meters. So this is going to be in Henry finally, okay? This you are going to get 0.0887 Henry. Find GMD and GMR of the following configuration. The line is completely transposed and radius of each conductor is 6 millimeter, okay? So here this configuration is given and the distances are also given, and you can see that this is a double circuit line. That means there is 2 conductors per phase. Here for A phase you have A dash. For B you have B and B dash. C is C and C dash. So we will see how to find the geometric mean distance. Since the line is completely transposed, the GMD for any phase is the same, okay? So we will take the phase A and we will find out. First, GMD of phase A when in position 1, right? That means in the present position, no change. So this is equal to the distance between A and B, A and B dash, A and C, A and C dash. Similarly between A dash and the rest of the conductors. So A dash B, A dash B dash, A dash C and A dash C dash. How many terms are here? You have 8 terms, right? So you have to the power 1 by 8. So now we will see what are these distances. First, DAB, this is the distance. So it is not given, we have to find it from the given data. So this distance is given as 3 meters, right? And this distance is also given as 3 meters. Now since this all will form a rectangle, this length will be equal to 5 meters, right? So this is equal to 5 meter. Since this is all symmetrical, this distance and this distance will be equal, right? So the remaining 1 meter will be divided between these two. So what will be the left out here? 0.5 meter will be left out, and this is also 0.5 meter. So here you have a right triangle, and this is the distance DAB. So what is DAB? This is equal to root over 3 square plus 0.5 square. Okay. Then DAB dash. So A is here and B dash is here. Here also you again have to form a right angle triangle. So this is the right angle triangle. So what will be DAB dash? This will be equal to this length square plus this length square. So this will be equal to DAB dash is equal to root over 3 square plus 5.5 whole square. Okay. Then what about DAC? A is this and C is this. So this distance is nothing but 3 plus 3. So you are going to get DAC is equal to 6. Then DAC dash. A is here, C dash is here. So DAC dash is already given, which is 5 meters. Okay. And what about DA dash B? A dash is here and B is here. So this distance will be same as this distance. Okay. So that is this. So here you can write DA dash B is equal to DAB dash. Then what about A dash B dash? This is same as AB. So here you can write DA dash B dash is equal to DAB. Then finally DA dash C. So A dash is here and C is here. This is 5. This is same as DAC dash, right? So this is equal to this. Similarly, DA dash C dash is equal to DAC. So now if you substitute all of these values here, we will call this GMD A1. You're going to get 4.88 meters. Next we have to find out GMD of phase A in position 2, right? So this is same as GMD of B in position 1. So that we can find out with respect to B, GMD with respect to B. Okay. So in this way we don't have to redraw the second position all over again. Okay. So here DBA, DBA dash, and then again from B dash to A, DB dash A, DB dash A dash. This is between A and B. Similarly, you will have DBC, DBC dash, and DB dash C, DB dash C dash. This is also similarly to the power 1 by 8. Now what is DBA? This is DAB, same as DAB. So we have already found this out, root over 3 square plus 0.5 whole square. Root over 3 square plus 0.5 whole square. And DBA dash, B is here and A dash is here. This also we have found out, right? So in this manner you can substitute each of this, right? And you are going to get the final value I am writing 4.36 meters. So this is GMD of phase A in position 2. Similarly, GMD of phase A in position 3. This is same as GMD of phase C in position 1. Okay. But here you can see this is position 1 and this is position 3, and both of them they are in a similar manner. Position 2 is a little different, but 1 and 3 are same. So you are going to get this to be the same value as GMD A1, that is 4.88 meters. So then you can find out the equivalent GMD as the geometric mean of each of these geometric means, right? A1, A2 and A3. This is because it is a transposed line to the power 1 by 3 because there are 3 terms. So this expression, if you substitute all these values, you're going to get 4.7 meters. This is the final geometric mean distance. Next we will find the geometric mean radius. So GMR, similar to the GMD, we have to find in each position. So GMR of phase A when in position 1. So what will this be? GMR A1 we will take. So D of A with itself, A with A dash with A and A dash with itself, right? To the power, how many number of terms are there? 4. So to the power 1 by 4. So this is equal to DAA is nothing but R dash, and what will be DAA dash? Here AA dash is here, right? We need a right angle triangle, so we will take this right angle triangle. So this distance is how much? It will be 6. This distance is 5. So what will be DAA dash? It is going to be root over 6 square plus 5 square. Similarly, DA dash A is also the same thing only, and DA dash A dash is R dash. So you can basically take this as square, and this entire thing will have to the power 1 by 4. Now what is R dash here? This is 0.7788 into radius, which is given as 6 millimeter. So 6 into 10 to the power minus 3. So this you have to substitute here. This, if you simplify, you are going to get 0.191 meters. Okay. Similarly, what is the GMR of phase A in position 2? This is nothing but GMR of phase B in position 1, right? So this is also in a similar manner you are going to get R dash into DBB dash. This will be whole square to the power 1 by 4. Now what is BB dash here? This 6 meters. This, if you substitute, you are going to get 0.167 meters. Okay. And what about the GMR in position 3? This is nothing but C1. So this will be same as GMR A1 because position 1 and 3 are identical. So 0.191 meters. Now what will be the equivalent GMR? This is the geometric mean of GMR A1, A2 and A3, right? This is to the power 1 by 3. This you are going to get 0.182 meters.